Hey Fixsters, and welcome to the level 2 of the Google FooBar challenge. So I just got invited by Google to participate in this channel. This is so if you this channel happens if you Google some coding specific questions and somehow meet the criteria. So it's not obvious to me how Google decides who to invite and who not to invite. But it's kind of, they seem to use your search history and stuff to get to guess whether you could be an applicant for Google. So if you could be interesting to be an employee, to become an employee at Google. And so the first step is this challenge, and you get invited by this challenge, so you don't have to do anything but like code, search for certain commands. And so, for example, when I search for Python list comprehension something, because I wanted to write an article about this actually, so I did some keyword research, and then there was a pop-up in the Google screen, just transformed to a pop-up where they asked me whether I want to participate in the challenge, yes, no, or don't show me this again. I clicked yes, and then I just decided that I record my screen and just like complete the challenge with you guys. So if you want to participate with this, and just keep watching. This is like level 2. I've already published one video which was level 1, and I hope that you are a bit patient, because I want to share like my thought process with you as I'm solving these challenges. And I don't know the challenge in advance, so I'm solving the challenge as I go through them. Okay, so I know as much as you, and so I only know that this is the second challenge I want to participate. Okay, so Google, if you participate in this challenge, and Google forwards you to this like shell-like environment, you have the usual shell commands like ls, show the directory, and so on. And here you have two files, and if you look at these files, you type in cat journal, for example. Then it gives you a message like, success, you've managed to infiltrate Commander Lambda's evil organization and finally earned yourself an entry-level position as a minion on her space station. From here, you just might be able to subvert her plans to use the lamp chop doomsday device to destroy Bunny Planet. Problem is, minions are the lowest of the low in the Lambda hierarchy. Better buck up and get working, or you'll never make it to the top. Okay, so we need to join the top. Commander Lambda, the evil one, sure is a taskmaster, isn't she? You're being worked to the bone. You survived a week in Commander Lambda's organization, and you even managed to get yourself promoted. Hooray! Henchmen still don't have the kind of security access you need to take down Commander Lambda, though, so you'd better keep working. Chop chop. Okay, so we keep working. So this is like an overall storyline. Let's check what is in start here. Type request to request a challenge. Type help for a list of commands. Okay, so let's start with the next challenge. Request. Okay, we have the challenge is, the latest gossip in the henchman break room is that LampChop stands for Lambda's Antimatter Biofuel Collision Hadron Oxidating Potentiator. You're pretty sure it runs on diesel, not biofuel, but you can at least give the commander credit for trying. New challenge, numbers station coded messages added to your home folder. Time to solve 72 hours. Okay, so this is the day. Okay, remaining for number station coded message. Okay, initially I thought these were hours, but this is actually days. Okay, so I can be a bit more relaxed. I actually, today is like the same day when I got invited for this. I already recorded the second video because I thought I don't have too much time to solve all the 5 levels. Okay, but somehow, I mean, we want to reach level 5, and we are currently at level 2, so the challenge shouldn't be too hard. So let's check what is in my directory. We have a folder named number station coded messages. Let's go into this directory, number station coded messages. Now you can see here we are already in the directory. Let's see what's in there. We have always, as usual, so as in the first challenge, we can either submit Python or Java code. And I'm the Python guy, as you know. I also know Java, so we could also do Java, but like this channel is all about Python, so we are going to have a look at Python. Okay, so let's have a look at the README first. Number station coded messages. When you went undercover in Commander Lambda's organization, you set up a coded messaging system with Bunny headquarters to allow them to send you important mission updates. Now that you're here and promoted to henchman, you need to make sure you can receive those messages. But since you need to sneak them past Commander Lambda's spies, it won't be easy. Okay, so it will be about encryption maybe. Bunny HQ has secretly taken control of 2 of the galaxy's more obscure number stations and will use them to broadcast lists of numbers. They've given you a numerical key and their message will be encrypted within the first sequence of numbers that adds up to that key within any given list of numbers. So given a non-empty list of positive integers L and a target positive integer T, write a function solution LT. Okay, so we have a non-empty list of positive integers stored in L, list of integers, and a target positive integer T. We want to write a function solution LT which verifies if there is at least one consecutive sequence of positive integers within the list L. So you know what, I just take this and copy paste it quickly because it may be interesting for you to see. Okay, so where do I copy this? Let's just copy it in the editor for now. Sorry, but I'm doing this live, as you know, so challenge 2. Okay, so we want to write this function solution which verifies if there is at least one consecutive sequence of positive integers within the list L. That means a contiguous sublist that can be summed up to the given target positive integer T, the key, and returns the lexicographically smallest list containing the smallest start and end indices should be, where this sequence can be found, or returns the array -1 -1 in the case that there's no such sequence. To throw off Lambda spies, not all number broadcasts will contain a coded message. Okay, so there are some dummy messages and we should detect them as well. For example, given the broadcast list L as 43578 and the key T as 12, the function solution LT would return the list 02 because the list L contains the sublist 435 starting at index 0, for which 4 plus 3 plus 5 equals 12. Okay, so from 0, so the key is 12, so we want to add up those numbers starting from index 0 to ending in index 2 included. We want to add up them and obtain the key 12, even though there's a shorter sequence that happens later in the list, 5 plus 7. So we want to return the first one, right? On the other hand, given the list L as 1, 2, 3, 4 and the key T as 15, the function solution would return -1 -1 because there's no sublist of list L that can be summed up to the given target value T equal to 15. To help you identify the coded broadcasts, Bunny HQ has agreed to the following standards. Each list L will contain at least one element, but never more than 100. Each element of L will be between 1 and 100. T will be a positive integer not exceeding 250. The first element of the list L has index 0. For the list returned by solution LT, the first element of the list has index 0. Yeah, okay, this is clear. For the list returned by solution LT, the start index must be equal or smaller than the end index. Okay, makes sense. Remember, to throw off Lambda spies, Bunny HQ might include more than one contiguous sublist of a number broadcast that can be summed up to the key. You know that the message will always be hidden in the first sublist that sums up to the key. So solution LT should only return that sublist, the first sublist. Okay, we can add it like either solution.py or solution.java if you want to use Java or Python. And the test cases are, your code should pass the following test cases. Note that it may also be run against hidden test cases not shown here. Okay, so we have like, if you have the Python cases, solution, this list and 15. there's no, like, we cannot sum up a contiguous sublist to obtain the number 15, so therefore the output should be -1, -1. And here we have this second solution, 4, 3, 10, 2, 8, and we want to sum up to 12. There are two ways of summing up to 12, so we have these two numbers, they sum up to 12, and that's it, right? Okay, so only those two numbers sum up to 12. Okay, so we have indices 2 and 3, indicates like from list element 2 to list element 3 with index 3, we have a subsequence that sums up to your target key 12. And then we can use like the command verify and our file name to test your solution and see how it does. And when you are finished, then we just use submit to submit an answer. And if the solution passes the test case, it will be removed from your home folder. Okay, so let's check the other constraints. Maybe there's something interesting. I didn't check this for the first test. Okay, constraints Python. Your code will run inside a Python 2.7, Python 2.7 even sandbox. 2.7, why Python 2? Okay, I didn't use Python 2 maybe for 5 years or so. All tests will be run by calling the solution function. Standard libraries are supported except for BS2, crypt. Okay, I even can use some libraries. Input output operations are not allowed. Your solution must be under 32,000 characters in length, including new lines and other non-printing characters. So I guess we can achieve this. Okay, so let's have a look at the editor. So if you type help, you see the different commands we can use, and we can use edit, and then we open the file in the editor. Okay, so let's call edit, and the file name, it was solution.py. And now we must put our code here. Okay, so I open the execution time. Execution time is limited. Okay, yeah, it shouldn't take forever, obviously. Good. So the first, again, given a non-empty list of positive integers L, so the first one is a list of positive integers and a target positive integer T, write a function solution LT which verifies if there is at least one consecutive sequence of positive integers within the list L that can be summed up to the given target positive integer T, which is the key, and returns the lexicographically smallest list containing the smallest start and end indexes where this sequence can be found. The lexicographically smallest list, okay, containing the smallest start and end indexes is clear, but could it be that we have two solutions? No, we can have only one solution with starting from one start index, right? Because I mean, if we would have two different end indices, it couldn't be the solution. Maybe if you have integer 0, then of course we could also use the integer zeros. So if you would have a list like this, so I just typed in the list here, like say 2, 3, 4, and we would search for value 9, then we could have also a few zeros here, and I mean these sublists would also sum up to 9, right? But we only want to focus on this one because to include the lexicographically smallest one. So if you would like this list, if you would have these two lists, these two sublists, then this sublist would be lexicographically smaller than this one, right? Because it has less number of digits in or elements. Okay, so therefore we want to have the smallest start index. Okay, so let me think about this for a second. Good, so we will start off obviously with the first index 0. Okay, so we have a start index 0. Let's do this. Start with this one. And now we want to figure out, we want to subsequently increase the start index. Okay, now we try to sum Okay, for I in range start to the length of the list minus the length of the list, because it's excluded. Yeah, the length of the list is excluded in our range, in the range function. So we go from our current start value, which initially is 0, to the end of the list in the worst case. And this will be our stop. Yeah, so let's call it stop. Our stop starts with start and ends with the length of the list. So I'm just thinking, should this be start plus 1 or start? But I think it can be start. I mean, so the stop index could be the same as the start index. For example, if you have the list, say we have the list 1 to 1 or so, 1 to 2, and we want to sum up to value t equals 1. Then our start would be 1, our start index would be 0, and the end index would also be 0, right? Because we want to have this whole sequence. So therefore it doesn't, it makes sense to start the stop index with the start value, and then just go all the way to the right, so that the stop index in the most extreme case, the stop index would be 0 or the length of the list. Okay, so we go all the way to the right, no matter where we are currently with the start index. And if the start index is the last element, it has index length -1, length from the list -1, and then if we go all the way to the right, we will just include this one element, which is also fine. Okay, so extreme cases would match, and now we check. Now we need to sum up. Yeah, so we need to sum if this sequence adds up to t. Okay, so we just called so if the sum of this sequence starting from index start, ending in index stop, if the sum is equal to our argument t, then we will return. What do we return? We return the start and the stop indices as a tuple or as a list. So here and returns the lexicographically smallest list containing the smallest start and end indexes where the sequence can be found. Okay, so it returns a list of the start and end indexes where this can be found. So like we have start and stop. I think we still have a small problem here, because now if we slice from start to stop, then stop will not be included in the subsequence, while our returned list should include the stop index in this sequence. Yeah, so we need to modify this and add 1 to the stop index here. So this means that we use slicing to slice from the start index to the stop index included. Okay, and therefore we add +1, because usually with slicing the end index or the stop index is not included. Okay, so now the stop index is included, start index is included, so we have this whole sequence. We return this list with 2 elements, the start and the stop index, but only if the sum of this whole sequence is t, adds up to t. Okay, so we can remove this one. Could this already be it? Of course, now we need to have this whole, we go over the whole. So what are we doing here? We start with index no, this is not the whole thing yet. So we start with index 0. Now we go over all possible stop indices. And but what happens if we went all the way to the right? Okay, so let's open another shell so that I can show you. So we have a list, like some elements, 5, 7, 8, 2, 3. Now initially this one is our start index. Okay, and then we have then we test like the stop index. Initially stop index points to 5, then the stop index points to 7, points to 8, and always we sum up the whole sequence and test whether the result, the sum, is equal to t, our argument. So say t equals 10, for example, yeah, t equals 10, and now those two don't sum up to 10, those don't sum up, and so on. Okay, so they may not sum up to 10, and so at one point we haven't found anything. We reached this stop index here, and we haven't reached 10 yet. So what we are doing is we move on to the right, so one element to the right. So we go here, and we start this whole thing again. This is not very efficient because of course, I mean, if we have already summed over these values, and so for example here 5 plus 7, then this would already be 12. So there's no need of looking even further. Okay, but these are positive integers, right? So they are not negative. Yeah, it's positive integers. So we can, of course, we can like skip the remaining computation. Could there be something else? So we want to, can we have a start index? Let's make this a bit more, a bit smarter. Okay, say we have a start and a stop index somewhere. And now we move the start to the right, So I mean, of course, we should skip it if the result is 5 plus 7. Okay, so maybe don't do premature optimization. First, we need to have a simple solution. I have some ideas how we can improve upon this, but I think we can integrate those ideas in a moment. Okay, so we need to have an outer loop for, so while start smaller than the length of the list. Okay, so in the worst case, so in the most extreme case, the length of the list L. So in the most extreme case, we will the length of the list will be like the start index will have length of the list minus 1, and this is the last element of the list, so it points to the last element of the list, and then it tries to find the stop index associated to the start index. And then of course, if it doesn't find it, then it should increase the value of start. Okay, so we can have start plus equal 1. Okay, so in each time we execute this code snippet, we basically check for a given start index. Now we check all stop indices by just summing up their length. And yeah, if we at one point, I mean, we return the first value that sums up the first start-stop combination that sums up to the list, because we start on the left and we go all the way to the right, and this is the lexicographically smallest list. Then of course, if we don't find it, if you go all the way to the right for a given start index and we don't find it, yeah, like this one, we don't find the value t, then we simply increase the start index by 1. And now we again go all the way to the right with the stop index. Okay, and if we don't find it, then we do it like this. Okay, so this is like our strategy that we have, Okay, and now in the last final step, we even like have the start index as the final element of the list, and that's it. Okay, so this is what we are. This is like a very coarse, very brute force approach of doing it. And we should always start with the brute force approach, and then you can optimize if the solution is very inefficient. Then you can optimize, but don't optimize before that. There's no need. Okay, so this should already solve it. So if there is a solution, then it should be returned by now. But if there is no solution, then of course we want to return -1, -1. There's no sublist that can be summed up to the given target value. And now there is an optimized. So let's check first whether it works. So I just copy paste this to my shell. Then I try the test cases they offer. So the Python test cases, you see them here. We print solution 1, 2, 3, 4, and 15. And we print solution 4, 3, 10, 2, 8, and 12. Okay, so the first one, it indicates that there is no solution, which is the case. Yeah, here we have the first output is -1, -1. The second one is 2, 3. Okay, here it seems to work. But in their test cases, they have, like, they don't return a list, they return a tuple basically. So I don't know, but they explicitly said we should return a list, right? Would return a list. Yeah, -1, -1. Okay, so this seems to work, but now of course we have this problem. It's not a problem, it's only an efficiency thing, and it's so simple that I'm going to just implement it. I mean, if you start with, initially you start with this start index, and then you sum to, and then you like add this one and this one together. Now they have value 12, and 12 is already larger than our target value, or our key, 10. So therefore, it doesn't make sense to try the other and stop indices, right? It doesn't make sense to try this one. It doesn't make sense to try this one. It doesn't make sense to try this one, because already this smaller subsequence is larger than our key value. I mean, if we just add more and more values, then of course the sum is monotonically increasing with more values we add. So therefore, it doesn't make sense to add even more values. So then we can, so if the sum is already larger, we can abort this branch of computation. Okay, so this is a quick optimization. So we go from stop in range start length. Then we have the sum. Let's call it I cannot call it sum. Let's call it s. I just store it in the value in the variable s. If s equals to t, we return simply the start and stop thing. Yeah. If s is larger than t, this case could also happen. Then we simply break this whole thing. Okay. Because then we simply abort this whole for loop. Yeah, we don't check the other stop indices because we already know that it wouldn't be there. Okay, so because we have already, I mean, our value t, our sum is already larger than value t, so all subsequent sums will also be larger than our key t. So therefore, it doesn't make sense to do something. Let's copy this and try the code. If it works also for the test cases. It's slightly more complicated code, but it returns the same value and it's more efficient. Runtime complexity. So we go over all elements. I mean, in worst case, it's quadratic runtime complexity, right? So I'm pretty sure there's a linear runtime complexity solution for this, but I mean, this one should be already enough for most cases in practice. Okay, so now we have this. I think it's efficient enough. At least we like included the low-hanging fruit, and so let's go again. It's very important for these type of problems that you really nail down all the edge and border cases. Okay, and therefore we will just read over it again, whether we have checked all cases. Okay. Given a non-empty list of positive integers L and a target positive integer T, write a function solution LT which verifies if there is at least one consecutive sequence of positive integers within the list L. That means a contiguous sublist, which we have. We have a slice with step size 1, so it's a contiguous sublist. And that can be summed up. And we use the fact that it's positive integers. Because if there would be a negative integer like here, -2, then of course we could not use our optimization. We could not abort this whole computation prematurely. Because even if we are larger here with these elements, we could obtain a smaller number later if we have some negative elements, okay? So therefore, it makes sense. So we utilize this fact that we have positive integers. Within the list L, that can be summed up to the given target positive integer T, the key, and returns the lexicographically smallest list. So it's the lexicographically smallest list, yeah? Because we return so we first look at the start index, we return the smallest start index, and then if there is a tie, we return the smallest stop index, okay? So because we return the first stop index found. So even if there would be a few zeros coming later, which you could also argue is a positive integer L, then those zeros would be excluded. And end index where this sequence can be found, or returns the array -1 -1 in the case that there is no such sequence. Okay, so this could also be the case. So sometimes we want to have this one. For example, given the broadcast list L, blah, 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 and the key T, the function would return the list 0, 2, because the list contains a sublist, and so on. Okay, so this we did. Each list L will contain at least one element, but never more than 100. Each list L will contain at least one element. Yeah, okay, this is a good thing. Then we don't have some border cases. I don't think that we would have a problem if it contained 0 elements, but anyway, so we don't really need this one. Each element of L will be between 1 and 100. Okay, so we will have a sum that is at most, so we could use this for more efficiency, because if our sum would already be larger than 200, forget about this. Each element of L will be between 1 and 100. We also don't need this actually. T will be a positive integer not exceeding 250. Okay, T will not be exceeding 250. So if T is already, so we could also have this optimization. L if T larger than 250. S is larger. Okay, this doesn't make sense. We don't need this because we already checked whether S is larger than T. But we already know that T is like at most 250. The first element of the list L has index 0. For the list returned by solution LT, the start index must be equal or smaller than the end index. So I'm not sure why they give us the numerical constraints of this problem. There could be something way easier. Let's check whether we could improve this somehow. So here we sum. I think it's a good. So this break will just end the loop prematurely. And start increases by 1 each time we enter this. So I think it's a clean solution. It's not a Python one-liner, but I mean, in some cases it's better not to write Python one-liners, and I think in this case it's easier to understand if you don't use a Python one-liner. Okay, let's try to break this code. So what happens if you have like so let's remove this one. What happens if you have 250 here? Should not be a problem, right? Then we don't find it. If you have an empty list, then we don't find it, so it doesn't matter. If you have a list with one element, 250, then it will find from 0 to 0, which is like the true case. If you have a So a few zeros, trailing zeros, doesn't matter. What happens if you have a few of those? Then it should return the zeros, yeah? So we sum from here, it must, so it could also start from here, but we should return the lexicographically smallest sublist, okay? So we start with from 0 and go all the way to the right until we reach the point. And of course this 0, 2 is lexicographically smaller than this list. Both would be a solution to the problem, but this one is lexicographically smaller, so this is the correct solution. Okay, so this, it seems to work. So our solution simply works, and I think it's efficient enough. Let's think about this, if you can find a quick optimization. So I think about something, can we have the start pointer and the stop pointer, and then we just, like in each step, we somehow reduce the stop pointer and increase the start pointer also. There could be something, I mean, we could have the start pointer, the stop pointer pointing at one element, then we go to the right with the stop to the right. This could be a nice solution if you have like the following algorithms. So we say we have the list, this one. Now we have the start pointer here and the stop pointer here. Let's call it like stop somehow. I don't know why I use this symbol, but okay. So I just use this thing. Okay, so we have the start pointer and the stop pointer pointing to the same thing. Now we check the sum. And if the sum is too small, then we increase the stop pointer by 1. And if the sum is equal, of course, then we return. So as long as the sum is too small, we increase the stop pointer by 1. And so t equals, for example, 5, 8, 10, say 10. So at least as long as it is too small, we simply increase the stop pointer. And then at one point we may find it already. Okay, then we simply return it. But if this partial sum that we have just calculated from the stop pointer, so for example in this case, if it is 11, and now we need to make sure that we have a value 6, so that if 11 is even possible. Okay, now in this case, so the sum of 5 is smaller than 11, so we increase the stop pointer. The sum of those two is still smaller than 11, so we increase the stop pointer by 1. And the sum of those is still smaller than 11, so we increase the stop pointer here. Now the sum is 12, so we have our stop pointer here with this symbol, so this is our stop pointer. And now the sum of those is 12, so it is larger, this subsequent is larger than our searched key. Okay, and as it is larger, we need to, I mean, it doesn't make sense to include more indices here, so we need to include less. Okay, so we cannot move one step to the right with a stop pointer, because this would just increase our sum. So therefore, we reduce the size by 1. We move one position with a start pointer. Yeah, so we move with the start pointer here now, and we remove everything else here. Okay, so now we are with the start pointer here, and now we calculate the sum again of this subsequence. And if this sum is smaller than our target value, 12, then we will increase it by 1. Yeah, this is the only way of making it larger at this point, starting with the start index. There's no other way. Okay, if it is larger, then it doesn't make sense to increase the stop pointer. So therefore we need to go like one step further with the start pointer. So this is an alternative solution, and I find it much prettier, this solution actually. Okay, so let's call this solution 2 and implement the first solution. Okay, so we have a start pointer and a stop pointer. Initially they both point to the index 0. Okay, start and stop, they point to index 0. And now we don't so what do we even check? So in each, so we have only one loop. In each step of the loop, we check, we increase either the start or the stop pointer. And so for example, while stop, we want to keep start and stop. Start must be smaller or equal than stop, and stop must be smaller than the length of the list. So let's write it this way. We could also write it the other way, a shorter way, but I think this should work as well. So remove this part. Okay, now we know that like start and stop indices, they are valid, yeah. So they can be the same, of course, but they can be also stop can also be larger. So but stop needs to be at least start, and stop needs to be at most the length of the list minus 1, and then everything else is fine, yeah, because we start with and stop with 0. Good. So then what do? We check the sum. So we calculate the sum again of the list. So this is basically this command. We check this sequence. Now we calculate the sequence. And now if the sum is equal to t, then what do? We return this thing, yeah. Now another case could be that the sum is smaller than t. If the sum is smaller than t, then we know, I mean, the only thing we can do is to increase the stop index by 1. We cannot decrease the start index by 1 because we have already checked it for all cases with a smaller start index. Okay, so therefore we need to calculate stop plus 1. So the stop index we increase by 1. If the sum is larger than t, then it doesn't make sense to increase the stop index even more because the sum will only become larger and larger. So therefore we increase the start index by 1. Okay, now this is a much more, I like this algorithm much more because now it's linear runtime algorithm. So we touch, so like the start and the stop indices, they touch every list element at most once. Maybe less, but at most once. So therefore we have linear runtime complexity. If the list has 1 million elements, we just touch 1 million elements basically, or 2 million elements. Yeah, but I mean it's linear in the size of the list. Okay, and so we don't have to do some ugly break stuff and so on. Yeah, we have a very, and if we don't find anything, so if we find something, then we return start stop. If we don't find anything, then we return -1, which is like the criteria that should be used. Okay, so let's remove this solution 2 thing and call solution. So what are the test cases? This one is one test case. So you know what, I will keep this solution so that I will keep this as a solution because I want to show in a later course, I want to show the bad solution, which was this one, and I want to show the more efficient solution, which is this one. Okay, so let's test some cases. Constraints. Okay, so this is one case. Now where is it? Okay, we want to have this case print 1, 2, 3, 4, and 15. And we want to have another case print like 4, 3, 10, 2, 8, and 12. And we have a problem else. And so, yeah, of course, we want to have an elif. And this one can be then else. Okay, I mean, this doesn't make sense, of course. So now in this case, we know that S is larger than t, right? Because it's not equal to t and it's not smaller than t, so it must be larger. And this should be an elif. Okay. Cannot unpack. Okay, so we cannot do this. Start. I think I searched for this notation. And now I want to have the solution of this. So there have been a few smaller code mistakes. So like conceptually the algorithm works, and then of course we need to ensure that it also runs. Okay, so the first test case should return -1, which it does, and the second returns 2, 3, which it does here. And our like extreme case should return 0 and 2 here. And if we like remove these leading zeros, then it should return 0, 0, which it does. Okay, so this is much more efficient solution. I like it more. So we simply use this one. It's also a bit shorter. And yeah, that's it. Linear runtime algorithm. We increased it by 1. Now we have found a solution. Now let's again have a look at our files. So we save the changes. Now we can call here in the command, you see you can verify a solution. So let's verify a solution. Let's verify our solution.py. So there was one test that failed. Interesting. So what if t okay, we stop, return start and stop. Start is smaller than stop, but it can also be equal, right? And if stop is small, stop must be smaller than length, right? If stop is equal to length, then we have a problem. Have we missed something in the constraints? Let's check. First element has index 0 for the list return start index. For the list returned by solution LT, the start index must be equal or smaller than the end index. So we make sure that the start index is equal or smaller than the end index, and the end index is smaller than the length. So in some cases, could this be a problem? I don't think so. I don't think that this is this must be a problem. Okay, so this is like very usual that we have some debugging going on. Let's again read the constraints. Cat constraints. Start with, so let's go back to the code. What is the problem now? If the sum is smaller than t, we need to increase the stop. Index to increase the sequence length. If the sum is larger than t, then we need to increase the start index, right? And we go from start, so we sum over all values from start to stop. So it must be a border case. Stop smaller than the length of the list. Yeah. I mean, our solution also works if t if t is larger than 250, for example. And our solution will also work if we have more than 100 elements, but I don't think that they want me to check this, right? So what happens? The start index must be equal and smaller than the end index. Okay, so what is the problem here? So we return the first sequence that sums up. So this is correct. So in the most extreme case, stop will point to the last element of the list, to the last index of the list. And now we calculate the sum from start to the last element plus 1. Last element plus 1, so we have the length of the list plus 1. Length of the list minus 1 plus 1 is length of the list. So now we slice all the way to the right, basically, which is fine. And we sum over all these values. So what other cases are there? Is there another case we have not checked? Given the broadcast list, so say we have this list. So we have another test case. Let's check this test case 4, 3, 5, 7, 8. And the key is 12 as well. Then it should return 0 on 0, 2, which is the case. Because list L contains a sublist 4, 3, 5. Starting at index 0 and ending at index 2. Okay, so we did this. And there's no sublist of the list that can be summed to help you identify the coded broadcast. So what happens if you have a list with only one element, like element 4, and our value is 4? Okay, now this seems to be okay. If our value is 5, then we won't find anything, and it should be -1, -1. If we have, even if you have 0 elements in the list, it works if you have 100, 260. So this of course would clearly violate. Okay, so I don't know. I mean, of course, I mean this solution is more powerful because it allows some cases they argue will not actually happen. So let's check. Each element of L will be between 1 and 100. So let's maybe add these checks. Check validity of input here. If any element of the list so could we do something like this? L x is larger. So if like we go over all elements in list, and if each element is, if one element is larger than 250 for x in the list, then we return -1 -1. Each element of the list will be between 1 and 100. No, actually, if any element will be smaller than 1 or larger than 100. Okay, if this is the case, or t larger than 250, the first element of the list L has index 0. Okay, the list returned by solution start index must be equal or smaller than the end index. So in these cases now we return -1 -1 because they are not valid according to them. Let's check whether this was what they were looking after. I cannot actually imagine. I don't think that this is a problem, but let's check. Save changes. Okay, test 4 still failed, so this was not a thing. And somehow I'm glad that this was not a thing, because this I would be really disappointed if this was a problem. Okay. So there's a test we fail. Let's check whether this solution actually works. Save changes. And we verify the solution. Okay, now this solution passes all test cases. And here you see that stop can actually take the... Okay, so what is the difference between these solutions? Let's compare them. So there's one test case that works for this first solution. And the other one, I mean, for our more efficient solution, it doesn't work. Okay, so we increase the start index. Start is smaller than length at each point. Okay, start is smaller than length. So this is also the case in our setting. And stop goes from start goes from start to the length of the list. So as start is always smaller than the length of the list, stop will also be smaller than the length of the list. Okay, so stop will be smaller than the length of the list. Now we sum up from start to stop plus 1, which means that if So we sum up to the stop index included. And now we check if s is larger than t. If the sum is smaller than t, then we increase the stop index by 1. And we try again. Next time the sum will be larger. And what if we otherwise we increase the start index? So we already have a solution, but I want to like make this more efficient solution. I want to make this work. Here we increase start in each iteration. Here we increase start. Okay, so in this case, so it could happen that if we start with 1, now I may see the problem. Okay, so what happens if we like start with this sequence? So we have the sum is smaller, the sum is larger. So say we have this sequence, 2, 3, 4. And our value for t is 6, for example, yeah? Now we start with this one and stop with this one, and our sum is already larger. So our sum is larger than our searched value. So therefore it will go into this setting. It will start so it will increase the start index by 1, but the stop index will still be larger, so it will just abort the computation. So of course we need to, now if we move the start index, then we also need to move the stop index by 1. We cannot keep it there actually, yeah. So I mean, so the stop index should be at least the start index. If the stop index is smaller, then this doesn't make sense because now we have an empty sequence, right? So the stop index should be at least the start index. So we have like stop is the max of start and stop. Okay, so if the stop index is smaller than the start index, then we simply set it to the start index. Okay, so this ensures that we move on to the right. Okay, so now this should work, right? So let's check for our solutions. We still have the same output, so still have the same solution, but now this should actually change things a bit. Okay, so what we need to copy this whole thing. Solution LT and solution LT. Okay, let's check whether we pass the test. Save changes and verify solution. Okay, okay, now it works. Now we have a beautiful solution, and we ensured. I mean, the problem was that the start index. Of course, if the start index. Let's go to our drawing board. Okay, so we would have like in this scenario where we have like a very large value here, for example. Now initially both pointers would point to this 255, but now say we search for the sum 5. Yeah, this is our value for t, and now we would see, okay, the start and the stop index, they are two. The sum is smaller than. The sum is larger than our searched value t, so therefore we need to move the start index by 1 position to the right. This was our solution, right? So we would have moved the start index, but now the start index points to the second element in the list, and the stop index still point to the first element of the list. So in this case, our sequence would be empty. Yeah? So we slice from here to the stop index, which is actually smaller, so the sequence is empty. But actually the start and stop index, they should at least point to the same element in the list. Okay, so it can be that the stop index goes further, but it cannot happen that the stop index goes is on the left of the sequence. Yeah, this doesn't make sense because then we would have an empty sequence. So the stop index must be at least the start index. Okay, so that's it. Now it took some time to figure out, but we have still plenty of time. We still have 2 days, 22 hours remaining or so, so it took us maybe half an hour or 45 minutes or so to pass this. And I hope that you learned something out of it. These are the kind of questions that got asked by Google, obviously, and also in the code interview. Then you should be able to answer them. And yeah, if you want to improve your Python skills, then you are at the right place. Check out the Finster material. We have a lot of those like tricks and techniques, and also the Python one-liner book, which I just published. They handle similar topics like this, so how you can solve problems in practice. And of course, as you saw, solving problems in practice involves trying things out and diving deep into the code. It's messy, but then sooner or later you will figure it out if you just keep pushing long enough. Okay, thanks for watching this video, and see you in the next video. Maybe let's submit a solution so that you can see what happens. Yeah, submit. So now we submit our solution.py. First we save the changes. Changes are saved. Now again we verify. Okay, now we submit solution.py. We are sure we want to submit. Okay, so now successfully we have completed in 1 hour, 3 minutes, 23 seconds. So it took an hour. Our current level is still 2. We have 1 challenge left to complete the level. Okay, so it consists of 2 levels. So I will record this later. I will come back at a later point in time to complete the challenge. But I think it's a very good. So Google really did a nice job of getting to know their employees and testing the skill level of their future or potential employees. I mean, I think even if I would pass this test, they would still ask me to do the coding interview and everything. So it's just like the first lead magnet, if you want, to get the leads, which are the employees, into their business. And I think it's a very, very sensible approach to find good people and people who are motivated and like coding. Okay, anyways, thanks for watching this video, and see you in the next video. Bye.